Okay, welcome back. In the last video, we talked about the tree traversal, and you may say, why does the tree traversal important? So let me give you an example. And if we let me use the example of the registration system, and then say our chancellor wants to know that uh, at this point, how many of the students are on academic probation for the next semester? And then what do? We want to visit all the students, and for each of the students we want to get one piece of the satellite data, and that is whether this student is on an academic probation or not, right? So we want to touch all the nodes, and then for each of the students we want to grab the information on whether this student is on the probation, and then we want to get a total number, and we want to bring this total number to our chancellor. Okay, well, and it doesn't really answer the question we originally asked. That is, how do we do a quick enough search? Well, we are not interested, when we are doing the search, we are not interested in the total number of the people got have the academic probation. We are going to have one specific student number, and we want to do a very quick search, and based on that ID we are getting, or that key we are getting, we want to return whether this specific student is on academic probation or not. So how do we do that? Well, we want to make use of the property of the binary search tree. What is that? For all the keys on the left side, they are smaller or equal to the parent. And for all the keys on the right side, they are greater or equal to the parent. Okay, so depending on the key we're looking for, and then the parent, which is x. Well, first, oops, I think I'm showing you the wrong slide. My bad. Okay, this is the right one. So, well, this key is the key we are searching for, and this x is the root of the current tree or the current subtree we are searching. Okay, and then if this x is already a null, saying, well, this is already a empty node, so there's nothing here, so you are going to return a null saying, okay, this search fails. Or in another case, if key is exactly the key we are getting from the current node x, and then you are lucky because you have already found the node you are looking for, because that is a match of the key you are looking for. And other than that, you want to do a comparison between the key you are looking for versus the key on the current node. And then depending if the key you are looking for is smaller than the current key, and then you only want to search on the left subtree. And on the other side, if the key you are searching with is larger than the key of the current node, and then you want to search on the right subtree. Okay, so this is for the search. And let's see this example. If we are looking for the key as D, and then we are starting from the root, and then we know that D is smaller than F, so we want to search the left subtree, and then we will visit the root of the left subtree, which is B, and then D is greater than B, so we want to do a search on the right subtree, and ta-da, indeed we find the key D, right? Okay, and another example, how about we are looking for C? So for the C, if there is C, the C has to be on the left side. So we want to do a search here, and then we compare the B and the C, and then we say again, if there is a C, and then C will be on the right subtree, which is the D, and then we visit D, and then we know D is greater than C. So if there is indeed a C, this C will be on the left side, but when we go to the left side of the D, we will find there is a null, so it's empty. So we have already reached to this case. So X is a null, but we are still looking for a specific key, which is C. But in this case, since X is already a null, we want to return the X, which is a null, saying, we don't really have such a value. Okay? Oops. And then here is another version of the search. So we are still using the X as the current subtree we are looking for. We are searching on, and then the key is the key we are looking for. And then as long as X is not a null and the K is not the key on the current node, and then we want to do a search. So if K is smaller than the current key, we want to move the X to the left subtree of the current node, and otherwise we move X to the right subtree of the current node. So in either way, and there's no recursion here. Okay, so there are two different versions. This version, we are using a recursion. In this way, we are doing iterations, and by introducing the while loop, and then we don't have the recursion. And my question is, which of these two functions is more efficient? So think about that. We talk about this in our day 2 of this class. Probably you guys still remember. Okay, the answer is for the tree search, this version, the version you are seeing with a while loop, this one is more efficient. Why? Because when you are doing the recursions are a sequence of the function calls. When we are doing the function calls, we have to create a new memory space, and we have to the Python has to manage the parameter sent from the caller to the callee, and then when a function call is finished, and then we have to handle the return values. So those are all called what? The overhead of the function calls, right? So that they are all the additional costs. Even though we are doing exactly the same thing, we are using exactly the same strategy. But when we are doing the recursive function calls, there are extra costs. So even though in this course and we have been doing recursions a lot, we talk about how to write recursions and how we analyze recursive algorithms. And sometimes when we just come back to the basic iterations and remember, well, when we are doing the basic iterations, it's not really something bad. Actually, the basic iterations, they are a little bit faster. Okay? And then, well, how do we do the insertion? Well, we just now talk about how to do the search. And for how do we do the insertion, this process is really similar. Why? Because when we are doing the insertion, the very basic step is we want to do a search so that we find the right location to do the insertion. Okay, so this brings us back to the idea of doing the search, because before we do the insertion, we still have to do the search. We are searching for the right location. But there's one thing. Well, we have to use a trailing pointer so that we can know what is the former node we have just touched. And let me show you why we want to do that. Say, well, instead of searching for C, now we want to do an insertion of C. So we are starting here, and then we say, okay, if you are inserting the C, you want to insert that to the left subtree, right? So we go to the left subtree, and then from the B, we want to go next to D, and then for the D, we want to go to the C. Okay, now my cursor is here. We find a null on the left side of the D, and we find a null. What does this mean? This means, well, now this is the place to insert C, but we have a problem. Our cursor is here. Our cursor points to a null, but where are we inserting? We are inserting to the left subtree of D, right? So that's the reason we are saying that we want to do a trailer pointer, because our current pointer will follow this path, and then we will get a null. Now we find a right location, but we also want to have a trailer pointer saying what is the node I just touched, and then this will give me the D. So once my current cursor goes to a null, and then I want to use my trailer pointer, which is the D, and then saying, okay, I want to insert C to the left subtree of the D. That is the right location. That is the location I'm searching for. Okay? and then we want to put the C here. And well, now before we finish, we want to talk about the time complexity of doing the search and the insertion. So when we are doing the search or a insert, what is the time complexity? That is OH. Okay, what is H? H is the height of the tree. Because either we do a search or we do an insertion, what's the worst case? The worst case is we start from the very top of the tree, which is the root, and then we go all the way down. We follow the longest path, and then we go to the bottom. And then that is the full height of the tree, right? So anyhow, the worst thing it can be is we go to from the very beginning to the very end, and then we follow the longest path possible from the root to a leaf. That is the height. Okay. And then the next question is, what is really the height of a binary tree? And to answer this question, we want to consider the worst case. Well, what's the worst case? The worst case is if we have a total of n nodes, and then we put those n nodes into a tree, and this tree is really unbalanced, or this tree is really skewed to one side. So this tree only grows on one side, and then even though this is tree structure, for the root, it only has, say, the right subtree. And then in this right subtree, it only has another right subtree. So this tree only grows on one side. In this case, the height will be exactly n. Okay, this will be the worst case. Well, and what's the best case? Well, the best case will be this tree is fully grown. It's almost a complete tree, and you can consider the heap structure. Okay, if we have that, and then the height will be log n, and that is the good case for us. So later in the next few classes, and we are going to talk about how we can maintain a balanced or kind of balanced binary search tree. Okay, so after today's lecture, you want to do the reading of the section 12.1, 12.2, and 12.3, and then in the next class, we will continue talk about the binary search tree. Okay, so that's it. That's the end for today's lectures, and I will see you later. Bye bye.